Let's say we want to answer a set of hypotheses about these data. Say we want to know if the throughput using robots is more than 5 units larger than throughput from human schedulers. And say we want to draw conclusions with 99% confidence. Okay, so we know, or we at least had some inclination from that confidence interval that robots outproduce humans. So now we want to know how big are they outperforming them by? How much in throughput units are they outperforming them by? Is the difference greater than 5 throughput units higher for robots relative to humans? Well, I erased all the individual observations, but we saw this. We saw that the mean was negative 32.56 units. And the standard deviation, let's go ahead and write that out. That was 35.03. Okay? So what we saw was that the column of robots ended up producing larger numbers than humans. Okay? Larger throughputs for robots relative to humans. So the difference, human minus robots, was a negative number because this number, robots, was larger. Smaller minus larger gives us a negative number. Okay? So we want to know, is that negative number less than negative 5? Okay? Is that difference, is this bigger than this by more than 5 units? Okay? That means, is this minus this less than negative 5? Okay? So our set of hypotheses looks like this. Is mu sub d less than negative 5? Okay? Are robots outperforming humans by more than 5? Okay? That means humans minus robots less than negative 5. Less than or greater than, either of those imply something that's not equality. We know equality is in the null, so the contradictory statement must be in the null hypothesis. Okay? So now we just have a test statistic that we need to calculate. That is d bar minus this d naught value, this hypothesized value, in standard deviation units. Okay? How different is the sample evidence from the hypothesized value in standard deviation units? Okay? D bar here, negative 32.56. We're going to subtract from that a negative 5. And then we've got 35.03 over root 8, sample size of 8. Okay? If we work this out, we get negative 2.23. Okay, our test statistic, negative 2.23. Okay? So we can, let's use the p-value approach. Okay? We can use the textbook here because the degrees of freedom are 8 minus 1, which is 7. Okay? So we go down to the 7 row in our table, but we don't see this exactly. Okay? We see negative t associated with 0.025 in the lower tail, and that is negative 2.365. Okay? Here our value is in between. And on the upper side, it's bounded by a t of 0.05 in the lower tail, which is negative 1.895. Okay, so we've got two values associated with two different tail probabilities. Okay, these are the values on the axes. These are the two tail probabilities. That says that the p-value for this thing, for our test statistic, must lie between 0.05 and 0.025. Okay? Our p-value lies in between these two values. So if we wanted to draw a conclusion with 95% confidence, then our p-value is indeed less than 0.05. So we would reject the null and conclude that the difference here is less than negative 5. Okay? If we wanted to have a stronger amount of confidence, if we wanted to be 99% confident, for example, our p-value would be larger than the value of alpha, and that wouldn't work out right. Okay, let's also just look this up in Excel and find the p-value using Excel, using the appropriate function, the tdist function. And that gives us a value of 0.0305. Okay? So again, this p-value, that's a little more exact for our exact test statistic here. It is indeed in between 0.025 and 0.05, and we know it a little more exactly. We would still draw the same kind of conclusion here. If we want 95% confidence, we would reject the null and conclude that robots outperform humans by more than 5 throughput units for each one of those, or for on average for a task.